Thanks for reminding me of that, Amber. All right, so now I'm recording an example, a pair of examples for searching. And what we're going to do first is set up a list that we can search for items. In order to do this, the simplest thing to do is to create an integer array. And I'll just do my classic and call it R. And then I will set it up as a new integer array. And we'll just start with 100 items in it. It's not too many, and it's pretty straightforward. I'm going to set up, one of the reasons I like to demo this is I like to show a couple of short tricks. One thing is if you need an array of integers set up randomly, then it's not particularly hard to do if you have a random number generator. And I'll init a random array, and I'm going to actually rename this. This is going to have to be sorted, so I want to make sure that it's sorted. And what I want to do here is I'm just going to do a for loop, and for every item in the array, I want to add a number. And so what I want is to start at a base number and then add a random number to it every time. So I'm going to set up an int, and I'm just going to call it current number, and we'll start it off at 1. And then what we'll do is every time we loop, we will add a little bit to that, and we'll move on. So I want R at position I to be equal to current number, and after that, I'm gonna current number plus equals rand dot next int, and in this I'm just going to put a small number like 3, so it will add 0, 1, or 2 to that number every time, and then it'll use it and it'll just keep going. In fact, instead of starting at 1, I'm actually going to start it at this. I think that's a little more entertaining. That way it'll start out at 0, 1, or 2. And everybody understand how I'm populating this array? It's just dumping a bunch of numbers in it. But I'm doing this in a sequence so that they're guaranteed to be sorted. And now I can when I'm done with that, now I can start sorting for specific numbers. Of course, the moment I see this, I also want to print it. And this will enable me to do that very quickly and easily. And there's nothing wrong with practicing with this. And I made a mistake up here. You never give the data type in an argument. You give the data type in a parameter. So let's do FOR tab, and let's just print these r.length, and we'll s out r at position I plus a little bit of space, just to pop the numbers back. Let's I was going to put a comma, but let's not for right now. This will shoot them all the way across. This might actually be a little bit long. Let's do a quick look and see if it's kind of stupidly long on the screen. And then, of course, assuming that it works. Oh, well, since I did the print line, that's not true. It just printed down. So that's kind of hilarious. I wanted it to be across. Did not do it right. So yeah, it is a little stupid long. This is what I'm going to do. Every time I print, I'm going to do a quick check. If I mod, let's do, I'm just looking at the screen here and measuring it by eyeball alone, how long I think it's going to be. Let's just do every 20. If I mod 20 equals 0, then I've hit a number that's divisible by 20. And if that happens, I'll just print another line. And this way it'll drop down and make it a brick of numbers instead of a ridiculously long line. And even though it's a little janky because I haven't spaced it perfectly, oh, and I did the 0. Yeah, I don't think I care. For right now, I think that's okay. I want to do 21. Let's try 21. I think it's going to look even worse. It didn't make a damn bit of difference because this first one is 0. If I mod 20 equals 0. Sorry, I'm wasting. I feel like I'm wasting time on this, but I do want it to look sort of good. And it's not equal to 0. Because if it's equal to 0, I don't want it to print. It's printing that one right off the bat. And I don't like that. I want it to not do that. Illegal start of expression. I've got something wrong going in here. If I mod 20 equals 0. There we go. Let's look at this right quick. There, that's a little cleaner. So thanks for your patience. Wanted it to look good. And now we can see all of the numbers. And now we can declare an int. And actually, I'm going to do this while number is greater than or equal to 0. This will enable me to quit when I want to. Setting up this loop so that I can run through and just say, give me a number, look for the number, find the number. That's what I'm setting up right now. So sout, enter a number. I like to put a space after the colon, and I like to do this without a print line because then it shows up on the same line and looks neater. And then I will say number equals keyboard dot next int and grab from the keyboard. And now I'm ready to search. So I've got my array of random numbers and I've got a number to look for. And so how do I want to look for this? The first thing I'm going to do is I'm going to do a sequential search. The sequential search is a very easy search. basically you start at the beginning and you just loop through looking at each number until you find it, and that's it. So let's get this done a little bit quicker, and I'm going to show you a couple of options here as well. So we will do public static, and in this case I'm just going to do bool. No, I won't. I'm going to do an int, which will tell me where it was found. This is pretty common. Sequential search, and I need what I'm looking at and what I'm looking for. All right. And the sequential search just works like this. You set up a for loop. You go through the array, right? You say if array at that position is equal to what you're looking for. If that's true, you found it. We can return I, which means that's where we found it. And if we don't find it, we can return -1, which means we didn't find it because that's an invalid index. Everybody with me on this? Anthony, Brendan, you okay? Amber?
Yep. Can you hear me?
Yeah, I can hear you. Is that Brendan?
Yes.
Sorry, I've called you Brandon a couple of times. I did not mean to. Sorry about that.
No, it's fine.
Okay. So I will check and then just say, actually, I will just S out. And then I'll just print the result of it. And this will allow me just to loop, 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 and pick a number, look for it, pick a number, look for it, and just see the result. And no big deal. And I will have already printed the array so we can see it. And if I enter a number that's negative, I'll look for it, I won't find it, and then I'll kick out of the loop and end the program. So it's a little bit quick and a little bit ugly if you ask me, but that's fine. Notice I didn't put a new line in front of enter a number. I should have done that. But let's just go ahead and test this. Might as well get a run out of it. And let's look for a number that's definitely there, like 10. So we type in 10, and it found it at 10. Well, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got pretty lucky with that. Let's look for another number. Let's look for a 1. That should appear at index 0. Let's look at 97. I'm doing edge cases. 97 should appear in index 99. That should be the last index. Oh, it found the first one. Sorry, there are 2 of them there. It found the one at 98. It always finds the very first one. And now let's do a number that's not here, like 9. And that should be -1. And let's do a number that's clearly not there, like 345. That's a 1. We can look for 77. That shouldn't be there, right? And then it's scrolling off, so let me pop this up. Let's look for a number that's there, like 72 is definitely there, so we should find it somewhere near-ish 72. I don't know where, but the numbers are going to be sort of close to their own index. So I found it at 70. So, and then I'm going to hit -45. It doesn't matter what the number is, as long as it's negative. It will not find it, and then I'll kick out of the loop. So sequential search basically plows through the list and finds a thing or doesn't. It's extremely brute force. However, it has one massively important feature. It does not care at all whether the list is sorted. You give it any array and it will work. So the beauty of sequential search is it will work no matter what. The negative part about sequential search is that it's very, very slow. If you had 5 million items, you would just plow through them one at a time. This is going to take forever. So binary search is a searching algorithm that operates much, much faster. But even though it's faster, it still it requires a little bit more coding. You have to know how to make it in order to get it to work. So anyway, so I'm going to show how to do binary search next, and we'll use a similar trick: public static int binary search, and we're doing the same thing where we're looking for an item called R, right? And then an int called looking for. All right. So we're doing the same basic idea. Now I should just be able to say binary search and click that. Well, actually, let me just leave that. There's no harm in calling that for right now. But do binary search like that. Now why this? Oh, because I haven't done a return statement. Just to get it to shut up. And now let's talk about binary search. I'm going to stop the share for just a moment and look on the board. And so sequential search, as we talked about, plows straight through. So we have just go through, look, find the thing, whatever. Brute force is guaranteed to work, but very, very slow on a big, big list. In order to do binary search, I like to look at it horizontally. And this is a very rough overview. You should have already seen the video and gotten a good explanation of binary search, plus the Zybook chapter. So I'm not going to go too much into detail. What I want to focus on is the code. But I still want to be able to say that if we had an array, what binary search does is establishes a low and a high. It's supposed to be the letter H, whatever the heck that was. And then it calculates a mid, and it looks at the mid. And if the mid is the one I'm looking for, then I'm done. If I'm not, then I need to cut out either the lower half or the higher half, depending on which side I know the sought item is going to be on. And then I reestablish the list. Let's say that I know that it's on this side, I can throw this away. I move my high down here, calculate a new mid, split it in half, and then I just keep doing this, moving the low up when I need to, moving the high down when I need to, and just chopping the list in half. Now, this is recursive because every time I look, I have a low and I have a high and I calculate a mid. So the structure is identical, but the size is smaller as I go. And this is why it's a candidate for recursion. And what this enables us to do is throw away half of our search space every time we look if we don't find the item. And this gives us a massive performance boost because instead of going, are you it? No. Are you it? No. Are you it? No. We go, are you it? No. Well, then none of these are either. And we can slough off massive chunks of our data space when we do this. Now, here's the problem. In order to do this algorithm, we have to call it recursively, and we have to give it a new high and a new low every time. Well, when I call the method initially, I don't know the search space, right? So let me go back to a shared space. Sorry, I'm getting over here. reshare this screen, pop back over. Notice when I'm calling binary search, I'm giving it the array and what I'm looking for. So I'm giving the whole search space and the thing I'm looking for. This does not include the low index or the high index, because why should it? Right? I'm giving you the array, you do the work. So the fun thing about binary search is that it's going to call a secondary search method. So my binary search is actually going to set up a recursive method. Now this one has everything. It has the array, it has the looking for, but it also has int low index. Okay, this is the index of the lowest part of the search space. And it has the high index. Now remember that the low index and the high index, these are locations, not values. So we're going to look at where things are we're going to look at the array using these indexes to see what is somewhere. Now, in order to call this recursive binary search, I'm going to return the answer that it gives me. Okay? And what I'm going to call it with is I'm going to call it with R. I'm going to call it with looking for. But to set it up, to get that initial recursive call, I'm going to call it with 0, because that's the low index. And I'm going to call it with array dot length, which is the high index. But the high index, actually, I need to take one away from it. So if it has 100 items, the high index is actually 99. So what I've done is I've put the burden of setting up this work, I've put it in the binary search algorithm. This is a prime example of abstraction. The binary search algorithm takes an array and a thing you want to look for, and it does all the work internally. I don't have to set it up. Okay, does everybody understand that? Remember, abstraction is the concept that you don't have to know how something works internally in order to use it. Well, if I make somebody tell me the first low index and the first high index, then I'm not following abstraction. When I call a search algorithm, what I want to do is I want to say, look in here for that, and I want it to do all the work. So I'm demonstrating how it can do that right now. The binary search method is doing all the work, but it's using its friend, the recursive binary search, because the friend requires setup and binary search shouldn't. So that's why I'm doing that. It's an example of the principle of abstraction. Now, the very first thing I want to do with this is I want to figure out what I want to do at each step. Remember, the whole idea of recursion is you're doing a smaller version of the same problem. We have to establish a base case. We have to establish recursive function calls, method calls, right? And we've got to figure out how to piece this together. So let's do that. This was demonstrated in the video, but I'm going to have to write these out or it won't make sense. So what we need to do is we need to establish a base case. The base case is the following. Is mid, actually, I apologize. It's not mid, because mid is an index. is the array value at mid, is that equal to what we're looking for? Sorry, I decided to write the G in looking before the K. Looking for. If this is true, we are done, and we can return mid. Then that's our answer. We found it, and we found it at mid. Does everybody understand? Okay, that's our first base case. Our second base case has H and L, have they switched places? So as we do this algorithm, low will get bigger, maybe. High will get lower, maybe. It depends on where the thing is. But these two will move towards each other in big leaps, actually, but they'll move towards each other. Eventually, we'll get down to one item. And if the item isn't found there, the next time we call, either the low index will move up or the high index will move down, and we will have a situation where the high index is lower than the low index. And that's another base case. So is the high index, right, is that less than low? If that's true, then we've base cased. All right, I should have stopped the share there, but that's at least I was able to say it. So that's what I want to do here. First, I want to mid index. I can go ahead and calculate it, and its calculation is the low index. I'm trying to get the middle plus the high index. Sorry, my throat's a little, need a sip of coffee to wet it. Okay. Divided by 2. This is integer division because these are all ints. So we add the low index to the high index, we divide it by 2, and we get the midpoint rounded down. It's always rounded down because there's never a 0.5. And now I'm going to do my base cases. All right. The first thing I want to do is I want to see if, and I'm going to actually check the false one first. If high is less than low, then, oh, sorry, it's high index, is less than low index. If that's true, then the item was not found. I ran out of space. So the thing was not in the list. And when I do that, I can return -1 to indicate failure. Well, it's not failure, it just wasn't found. And then I can do another base case, which is if our at mid index, if that is equal to looking for, then I can return mid index indicating that I found it. Okay, everybody okay with this so far? These are just our base cases, right? Amber, is this becoming clearer? Oh, I knocked the chat window down. I'm so sorry. I've been doing this thing without the chat up. So if you've been asking anything, I haven't been listening. Okay, unfortunately, no questions. Now, what I need to do is set up my recursion. My recursive base cases, there are only 2 possibilities. Since I know I still have space left, and I know I haven't found the item, what I want to do is to find out whether the item belongs on the low end or the high end or the high half of what I'm looking for. So this is what I want to do. I want to say if the thing I'm looking for, if it is less than the item that I'm at, right? If this is true, the thing I'm looking at is lower and it belongs in the bottom half. So what I'm looking at is too high, so lower high index. So I need to return the answer because I'm going to get an answer. And what I want to return is, I can't spell it quickly, recursive binary search. I need to give it R. I need to give it looking for. I need to give it the low index because that's the same. But because the high values can all be thrown away, I want to call it by reducing high index. I don't want to give the high index. I want to give the mid index, and I want to give the mid index -1. The reason I want to give mid index -1 is I've already looked at mid index, so that can't be it. So I might as well give mid index -1 as my top index. So that is what I do if the item is too small. So when I looked at the item, mid was bigger than what I'm looking for. I move high down. I do that by setting high index to mid -1, and I set it that way by modifying this. Now, when I reach this point, there is only one possible thing that can be true. I've triggered none of my base cases, so I must recurse. There are only two ways to recurse. One is to recurse by lowering the high. The other is to recurse by raising the low, because I have to do one of those. The last one is it must be that I have to raise the low index. So I can just write this like this: return recursive binary search, because I know this is all that's left. And I can again give it R, looking for. Now I want low index to be bumped up to mid index +1. And again, there's no reason for me to look at mid index again. So I'll bump over it. And then I give this high index. Okay. And this is the code for it. And I didn't put comments in here. Right. And this second one, I'll just pop this. All right. And then that's the binary search algorithm. Everybody fair enough with this? Please type any questions you have regarding like how it's working, because again, this is a classic recursive algorithm, and it's got all of the features. It's got the 4 questions are perfect, right? We've got the problem is being written as a smaller, identically structured version of itself. We can identify base cases, right? We've got 2 base cases. We found the thing. it became impossible to find the thing. Our recursive method calls approach both of those base cases simultaneously. As we look at mid, the search space gets smaller. We're getting closer and closer to the value we want. And the search space is getting smaller. So we're approaching our first base case, which is we run out of space. We're approaching the second base case, which is we're getting nearer to the item if it's there. And finally, our last question of recursion is, will we get there? And the answer is there's no way we can avoid it, because we're going to crash into either finding the thing or running out of space no matter what. So we're guaranteed to finish two. So this algorithm meets all the requirements. All that's left is to test it and to hope that it actually works. Of course, we'll see. So let's run it and see if I did it correctly or whether it crashes on me or whatever. Enter a number. Let's look for 5. We should find 5 at index 0, 1, 2, 3, 4. So we should get an answer of 4 from both of these. So I'll type in a 5 and it found it, right? And if I type in a 4, there isn't a 4. So both of these should generate a -1. All right, that's pretty good. Let's look at 97. This one should be a 99 for both of them because it's the last index and there's not a duplicate in front of it. Now, here's an interesting thing. These search algorithms don't work exactly the same. Sequential plows through just looking, but binary search hops and hops and hops. So fun fact, there are 4 12s in this list. When we do the sequential search, it will find the very first one. When we do binary search, we don't know which one we're going to find, right? It's going to, one of these 4 is going to become mid first, and then we will find that one. Do you see what I mean? Isn't that weird? So we will find a 12. So if there are duplicate items, these search algorithms potentially generate different results. In fact, there are 5 9s. So let's look for a 9 and see which one we get. So the sequential search found the first one, which was at index 8, and binary search found one at index 11. So the thing is, when there are duplicates, you're just going to find the first one. One problem with sequential search, but with both of these, is neither of them tells you how many there are. That's a more advanced search algorithm. So you could look for a value and it would count how many of them there are. In sequential search, you can do this easily. You just, instead of returning the moment you find something, you increment, and you just return how many of them are in there. With the binary search, it's a little bit trickier. Once you find the item, you'll have to make a new algorithm to kind of move in both directions, spreading out to find how many are next to it, because they're guaranteed to be right there, but you don't know how many of them there are. And if you want to know their positions, then you've got to return a lot more information. So you can see how finding items, like when you're doing a search and you just kind of say, find these items, it's actually pretty complicated to find like all of the occurrences of something. You need an array to store all of those, or an array list. So it can get pretty interesting. But if you can implement binary search, now I know that I just did it in front of you, and so did the gentleman who did the video. He did it in front of you. You can look it up. You can find binary search online. No problem, right? It's not hard. but the thing that you need to remember is if you can write it on your own, right? If you can go from here, your brain, into code, then you're doing really well, right? That's a good skill to have, because then you can create modifications of it. Even though an algorithm has been solved, that doesn't mean that it's a bad idea to know how to do it, because you might need to do that algorithm with a twist. And if you know how to do the algorithm, then you can implement a twist. And if you don't know how to do the algorithm, well, then you can't customize it. So anyway, that's why these algorithms are so important. Even though they are known, you still really do need to have them in your skill set. Every programmer should be able to write a sequential search and a binary search just like that. Now, they might have to think about it for a little while. I'm not saying instant recognition. You might have to remember how it works, right? But you should be able to build it on your own without much trouble. And that would be the expectation of a graduate, right? Job interviews are going to ask you how do you implement a binary search? And so you should be able to do that. They might even ask you to do it with certain tweaks, if that makes sense. So anyway, I would now open this up for questions. Brendan, you still there? Can you say something?
Yeah, I'm here.
All right.
I think Amber has a question in the chat though.
Okay. Yeah. So Amber asked this question, which is really important. If the array wasn't in order to use binary search, you would have to sort it. Binary search simply does not work in an unsorted list because the mid means nothing, right? The whole idea is that if you look at mid, if the list is sorted and mid isn't the one you're looking for, then you immediately know which side you can throw away, or at least you can find out. You use an if statement to find out, okay? But if the list isn't sorted and you look at any one of them, all that means is that that one isn't it. The directionality is no longer valid. So here's a tip. If you have an unsorted list and you want to look for something, and you're only going to do it one time, just use a sequential search. There's no point in sorting the array to look for something once. But if you need to look for things a lot, right? If it's like a phone book or, you know, I don't know, phone books don't exist anymore, but you get the idea. If it's a list of things and you're going to want to look for things a lot, or the list is really big and you're going to look a few times, then, well, it just depends. But the pain of sorting is pretty high. In other words, it takes a lot to sort a list. So you don't want to pay that cost unless you have a need to do it. So be aware of that. The sorting algorithms are time consuming. And you don't save time sorting an algorithm and using a binary search unless you're going to look for a lot of items, because you got to pay that sort price first. Another thing is like, let's say that you have you want to look for items and the searches have to be fast, but you have some time to prep. For example, you're going to get your data and you've got 5 million items and people are going to start asking you to find data, but you have a little bit of time before they start to sort the thing, then you're in good shape. Then just sort it. But just keep in mind the price of calling algorithms. That's why the big O notation is important. I cut it out of 150 because we just don't have time. But that's a massively important thing to know, and you'll pick it up in both 240 and in 340. But knowing the speed of an algorithm is super important, because then you know what price you're paying to run it and whether or not it's appropriate. If somebody gave me 5 million things and they said find one thing, and I would just set up a sequential search right away, because I don't know if it's sorted or not, and sequential search will work. And it's only one thing. It's just going to go through, whoop, and it'll find it, fine. But if I know that it's sorted, then I might do binary search. But if I'm only going to do one look, then who cares? So there's a lot of trade-offs, right? Anyway, I feel like I'm starting to ramble, which is my tendency. So I will now stop the recording.